Welcome to Complexity Made Simple. I'm Paul Allen, and the subject of today's newsletter is Design of Experiments. An alternative title, it's the fastest way to find out. If you have a technical problem and you're trying to make the best performance to come out of your process, I'm a manufacturing guy, so I'm going to talk about machinery today, but it could also be your marketing process, it could be your website, and you're trying to get the best performance, the best return from your process. Design of experiments would be the weapon of choice because it is the fastest way to find out. Now, what's your alternative to using tools, of course, when you're trying to get a machine to work, a website to work, whatever it is? You use skill and experience. You employ good people and you trust them. You trust them to find the best settings on a particular process. Well, what we're going to talk about first is why that's never going to find the best settings. Let me show you how complicated your processes are and what your technical people are trying to do. So the example we are going to use, let's just talk injection molding for a second. It doesn't really matter what the process is. This could be any technical process, any piece of machinery that's got settings, speeds, feeds, choices of material, etc. You've got to find the best settings. Let's have a look how complicated this problem is. So let's look at the variables that your skilled person might be having to play with. So we're going to go regrind. We're going to go from 0% up to 100% regrind. We're going to go material temperature. So the material temperature could be 200 degrees, could go up to 250. We're going to go fixed tool temperature. Could be as low as 14 degrees, could be as high as 60. We're going to go mold tool temperature, and again 14 to 60. Screw speed. Screw speed goes from 50 to 275. Injection speed. That's going to go from 10 to 100. Cooling time is going to go from 5 to 25. And finally, hold pressure is going to go from 100 to 500. Let's have a look. How many dials is our technical person dealing with? 1, 2, 3, 4, 5, 6, 7, 8. Okay, so it's 8 dials on the machine. He'll probably have this sorted out by lunchtime, I dare say, because it's only 8 things to play with. Not too tricky at all, is it? But let's look at how many choices he has to choose from. And don't forget, what we're interested in is the best settings, cheapest, fastest, best quality. I don't just mean settings that work. I know you can find settings that work. You are trying to smash the competition. You need the very best productive settings for that very expensive equipment that you're running. So let's take a look. How many choices has this guy got? Well, we'll start at the top. 100 multiplied by 50. Multiplied by, what's this? 46. He's got another 46 choices there. He's got 225 choices on the screw speed. Let's multiply that in there. 90 choices on the injection speed. He's got 20 choices on the cooling time, and finally 400 choices on the hold pressure. Now, in order to save a little bit of time, I made the calculation before I started the video 5 minutes ago. And there's my calculator. I'm going to just show you because I can't even read the numbers. I think it's something like 1,500 trillion choices. I think that's the number, maybe a few more noughts than that. Who cares? It's too complicated for your technical guys to even have a chance of finding the very best settings. It is way too complicated. And therefore what we're going to do is we're going to use some relatively simple maths. This technique has been around for 100 years and it's known as design of experiments. And we are going to now take a look at a case study that deals with this very particular problem. Hope you enjoy it.
Testing system, a very deliberate test on the process, known as a designed experiment. Now the first one that it says there we're going to do is a screening DOE. That's because we have lots of variables and we don't yet know what they do. So here is the screening DOE. Now just before we take a look at the test that's conducted here, I want to just think about how complicated the problem currently is. Because what do we have? We have 1, 2, 3, 4, 5, 6, 7. We have 8 variables there. And you'd think, well, it's only 8 dials, it's only 8 settings. It can't be particularly difficult to find the best settings. Now I know that you can find settings that work on a machine. That isn't what we're trying to find here. We are trying to find the very best settings, the fastest settings with the best quality. This isn't about a set of settings that just work. They already have that. Okay, so we are trying to find the very best settings. So 8 variables. Now it looks really easy, doesn't it? But actually what most people do is they only count the variables. They don't look at the number of combinations. So look at this. You have 100 choices multiplied by 50 choices, multiplied by 44, by 44 choices, by 225 choices, by 90 choices, by 20 choices, by 400 choices. If you multiply that lot through, this isn't 8 variables that you're looking at. And I've just worked this out on a calculator. Oh dear. It's 1.5 trillion choices. That's the complexity of trying to find best settings. This cannot be done with someone's skill. Someone cannot carry this model in their head and understand what the best settings will be to get the fastest process with the best capability. It just is not possible. Only DOE can interrogate that design space using mathematics essentially to interrogate that design space. One of the things I've included here, look, is regrind. Regrind is something that they don't currently control. Most companies don't control regrind simply because you never know quite how much you're going to have. So it tends to be a movable feast, regrind. So we are going to put that into the test because we want to see what effect it has on our process. One thing that's very important when you do a designed experiment, this is a very structured procedure. This is not just random tests. You are about to see 12 tests. So the designed experiment of choice is known as a Taguchi L12. It's a pre-designed pattern, and it is a pre-designed pattern to get the most information in the fastest time. That's why we do these things. We don't do them just to be mathematically perfect. You get the maximum amount of information from the minimum amount of data. So it's a very structured test. It's not just an engineer making up 12 experiments. That's not what's going on here. Anyone that did the L12 screening DOE would do an exact same pattern on their molding machine, on their packing machine, on a press, on a furnace, whatever it happens to be. The pattern is the same because the pattern is super efficient at getting information. So really important that we do a great procedure when we do this. You'll see how disciplined this team have been here in making sure that this DOE goes really well. Labeling all the parts. Very important that the parts are kind of well looked after, well labeled. All the data is important. If you miss one of these tests out, the other 11 are not as useful. So this is it's a very different type of testing to what an engineer would do, where he'd just simply have a guess, put some tests in, have a guess, do a test, have a guess, do a test. These tests all have to work together, so you have to follow the pattern. And here is the pattern. So there's the pattern. Key point about the efficiency here, as I mentioned, we have 8 variables, 8 settings. We are only going to do 12 tests, 12 setups, although obviously we are repeating, we are collecting a sample multiple times for that setup, but we're only going to set the machine up in 12 different ways. We've collected data on flatness because that's the area where we've got to understand how to get a flat part. Both cavities have been put together, as you see there. And we've also collected data at the same time on the cycle time. And here's the key point about this experiment as well. What this experiment is going to do is find the sweet spot. We want to go fastest with the best capability. Where is the sweet spot? That's what these experiments are going to tell you. Often you have engineers who know how to go fast. They can't get the quality. They know how to get the quality, but they have to slow the machine down. Where's the sweet spot? The sweet spot is so difficult to find just in your head. This is going to find the sweet spot for us. So out of that experiment comes some diagrams. For those of you that haven't seen these diagrams before, the marginal means plot. The longer these lines, the more influential the variable actually is. And what we often get is a graph that tells us how the variables move the average, how they shift the mean. That's what this is telling us. So for instance, the screw speed, look, has the biggest effect on the flatness. But it also tells us about the standard deviation. So do variables affect the spread? So does it affect the spread of this thing? So the mean, the middle here, wouldn't be moving, but the distribution of the results, the variability, is being reduced or increased. Now that is being driven here, look, by the holding pressure for flatness. So immediately we know how now to pinch the variability in for flatness. So they're the two graphs they're the two diagrams for flatness. And then we just have one graph for the cycle time, because of course the cycle time is completely repetitive. There is almost no variability in the cycle time whatsoever. It's computer controlled. But the biggest effect, you would expect these to be time related. Cooling time has a big effect. Injection speed, screw speed. they're all about speeds and times. They're bound to have an effect on the cycle time. So that's not too much of a surprise. But of course, we're trying to find the sweet spot. It isn't just that we know something, it's that we can find the best midpoint, the best settings. So as a result of those simple graphs, they've decided to holding pressure at 100, because that was the release variability for flatness. Screw speeds up at 200, material temperature 225, fixed tool temperature has gone to 14, and move-in tool temperature has gone to 60. So they fixed 5 of the variables just using simple graphs. Just took them 12 tests to figure that out. Yeah, so we've got the flatness now better controlled. We've got the cycle time going pretty quick. So looking good so far. Moving on, this leaves 3 variables that they haven't fixed. Regrind percentage, injection speed, and cooling time. Now these are going to go into what's known as a full factorial. A full factorial allows for a mathematical model to be created on the process. So rather than just using simple graphs like we just did, we're going to use some mathematics this time, because this is a DOE that allows that, a full factorial. So there's the DOE. Again, the pattern is important. They've reduced the high and the low down for regrind. So previously the high was up at 100%. They've decided to bring that in, and they've just gone to 50%, which is more likely to be what gets used out in production. So they've changed the design space slightly in the second experiment. So again, here's the data. Discipline test. We need to collect data on flatness. Only 8 setups, by the way. So let me just point out, we did a screening DOE. We did 12 setups on the machine. We've now done a further 8 setups. Okay, so a total of 20 setups. And from those 20, we're going to pick best settings from the 1.5 trillion that we had out there. This is a super efficient way of doing this. Cycle time and flatness. So again, we're collecting both of those, and again, we're looking for the sweet spot. Okay, and now what we have is a model. So for those of you that haven't seen it before, in this column here, that is an equation of how to achieve flatness based on regrind injection speed, cooling time. The interaction between these two and the interaction between these two is also important. So we have a mathematical model. We also have a mathematical model for cycle time. It's going to be a hell of a lot simpler, because typically speed and time are going to have a huge effect on cycle time. So the model on the right, not so important, but the flatness is a great model to have. We now understand the process really well. So what we're now going to do is ask the computer. Now it knows those 2 models. We're going to ask the computer. We're going to ask the computer to try and hit the 2 targets. So here are the 2 targets. We've asked it to come up with a cycle time which is less than 18 seconds. At the same time, we've tried to get a flatness which is less than 2.2 millimeters. So we've asked for those 2 things, and it said, you know what? Here are your settings if you want to achieve those 2 things. Let's have a look. So this was the before and this is the after. Look at the difference. Now we've put those best settings in. So we've put the best settings in from the screening DOE, the best settings from the modeling DOE. Just 20 tests have got us flatness that looks like that. That is just incredible, isn't it? Let's have a look at cavity 2. Now cavity 2, if you remember, was the one that was giving us the problem. Cavity 1 wasn't such a problem. So if we can achieve the same thing with cavity 2, then we're in good shape. Look at that. So now, process capability before, process capability after. Fantastic. We are pretty much defect free. And take a look at the numbers at the top. Look at the cycle time. The cycle time has come down by 4 seconds, 5 seconds. We've knocked 20%, probably more, off the cycle time, and we've increased the process capability. So let's have a look at the benefits. Now this is just the saving on manpower, but to be honest, it's probably a lot more. It's probably a lot more than this. Quality wasn't causing us a big deal. Look, it was 1.4% the old process, but now 0 defects. So we're going faster and better quality. So all the targets were met. We were aiming for 19.26 on the cycle time. We actually hit 17.49. We were aiming for the CPK of 167. We actually hit the CPK of 3. So we absolutely smashed the targets. We had 1.5 trillion choices. And we only ran 20. Only a DOE can find these answers so quickly. There we go. Total cost saving, 15.
Well, I hope you found that useful. If you've got any questions about that topic, or indeed anything to do with Six Sigma, or Lean for that matter, give me a call and I hope to hear from you soon.